Hello, everyone. Thank you again for coming to my talk. It is a great pleasure to speak to all of you. I'll be presenting WebAssembly is all you need, exploiting Chrome and the V8 Sandbox 10 times with WebAssembly. So a quick disclaimer, this is technically a 60-minute talk compressed into like 30 to 40 minutes. So the information might be dense. Please refer to the slides if you have any questions, and feel free to ask questions anytime after the presentation. Thank you. So who am I? I am a first-year PhD student, currently doing my PhD program in Carnegie Mellon University's Computer Science Department. And I was also a former research intern at Kai's Hacking Lab. I'm also an occasional CTF player. And I have been an independent vulnerability researcher as a hobby. I had the chance to demonstrate about 3 Chrome render exploits on Pontoon Vancouver 2024 and on TyphoonPWN 2024. I'm also playing actively on Google kernel CTF and V8 CTFs. So why am I giving this talk? I had this impression that finding and exploiting browser bugs are hard. But by saying that something is hard, we should be able to define what is it that makes it so hard. And for an attacker's perspective, how can we make it easier? And this naturally leads to the next question of, as a defender, how can we make these attacks harder? And I've also noticed a distinct lack of publicly available information on vulnerability research. So from this talk, I wanted to publicize knowledge and insights that I've gained to collectively advance vulnerability research. So yeah, this is the agenda. I'll first start with a prequel bug from Manfred Paul's bug demonstrated at Pontoon 2024. And we will have the chance to explain about the WebAssembly type system and the Isorecursive type system that they use. We'll continue on to a sequence of 3 bugs, where 2 are very closely related. And the first one is the bug that I demonstrated at this year's TyphoonPWN event. We'll finally continue on to the world of WebAssembly-based V8 Sandbox escapes, and we'll also take a sneak peek at the other browsers and future targets that we can look into in Chrome. So yeah, the prequel bug. To start with, there's a very good blog at the Zero Day Initiative's website, written by Manfred Paul himself. So I recommend you go and take a look later on. So yeah, this bug is, again, presented by Manfred Paul at Pontoon Vancouver 2024. This is a universal WebAssembly type confusion due to missing type count check. So to understand what this actually means, we need to see what WebAssembly types are. So what is a WebAssembly type? WebAssembly modules can contain type sections, which is just a list of module-defined heap types, containing things like function types, structure types, and array types. And each of these module-defined heap types has their own type index, allocated in increasing order simply by their order of appearance in this type section. And it is worth also mentioning that WebAssembly modules can have at most 1 million defined heap types. WebAssembly also supports a notion of recursive type system within a recursive group rect type. And then these rect type can contain multiple subtype members. Each of these subtype members are assigned a separate type index, but not to the rect type itself, simply because we don't really need to reference the whole recursion group. So yeah, word is cheap, show me the code, and this is how the code works like. We have 2 recursive group types, each containing 2 subtype members, and then a standalone type at last. These get allocated the type index of 0 to 4 incrementally. So the bug that we are looking at happens at these really a small fragment of code. This is where the type section is decoded, where we first decode the number of type counts that we are willing to decode. And then for each of these types, we see that if this is a recursion group or a standalone group. For recursion group, I've mentioned that these can contain multiple subtype members. So we need to validate that adding this much subtype members does not overflow the limit of 1 million. And this is indeed checked in the left side, as shown in the red box. However, in the right side, the code is shown for standalone types, which does not have this check, which is problematic because the type count itself is limited to 1 million, but each of these type counts can either be a standalone type or a recursion group, which can also contain type up to 1 million number of types. So yeah, the demonstration of this bug was extremely simple. You just create two types, two like top level types. One is a recursion group having 1 million subtype members. And the next is just a standalone type. So theoretically, this should not be validated, and this should like not even compile because we have 1,000,001 types. But in reality, this does compile and this does decode correctly. So exploiting this may not be straightforward at first because this is just like overflowing the limit of 1 million, and we shouldn't like do anything bad with that. The problem is that we have these generic heap types, which are defined with a type index starting from 1 million. So what are generic heap types? Generic heap types are demonstrated in this diagram, where there are just like supertypes and subtypes. For example, if we have a specific structure type defined in our module, its supertype is can be a generic heap type struct. It can also be something as an equality type. It can also be any type, and it is also a supertype of none type. So we have we can demonstrate the generic types as this diagram. The generic heap types that we will be focusing on is just like these 3 or 4 of them. It's an any type, which is a supertype of all WebAssembly internal types, structure types that we are interested in, and the none type, which are subtypes of all internal types. We are also we're also interested in the extern type, which are an opaque type, not like that the WebAssembly code does not care about. It's something like a JavaScript objects that the embedder can provide into the WebAssembly code. So the key idea of this, like exploiting this bug, is actually quite simple. Any concrete structure type, as we've just seen, is a supertype of none by definition, because none is a subtype of all WebAssembly internal types. And an object can always be upcasted to its supertype object, because they're just supertypes. We don't need a dynamic check for that. So what happens if, with this bug, we're able to alias a concrete structure type with the type index of a generic heap type, in this case, a none type? Then in this case, the type may be misrepresented as not the concrete structure type that we want to represent, but instead a reference to a none type. And we might be able to upcast this to any other types. So this 5 steps is literally what is required to write a full exploit. We first create the following 2 types. The first type is a structure type, a source structure type, which we, by using the bug, which we alias the index with the generic heap type index of none. The second is the destination type, where we want to confuse the structure type to the destination type. So the first 2 steps, 2 and 3, are just we push the field type and then just create a structure out of it. This structure is now typed as a reference to the source type. However, by this bug, this type is now indistinguishable with the reference to a none type, simply because the type index has aliased with the none type. So now the decoder thinks that this type is a reference to a none type, and then statically upcasts this to reference of our destination type, which we can use to fetch out the field index back. So looking at all of the code flow, it's quite evident that we're confusing a random field of source type to another random attacker-defined field type into the destination type. So this results in like a universal WebAssembly type confusion from the field type source to the field type destination. it's also interesting that with this kind of bugs, we can immediately acquire all JavaScript exploitation primitives. For example, confusing a reference to an extern type to a 32-bit integer grants you the primitive of address of. Going backwards, it grants you the primitive of fake object. If we take a detour and convert a 32-bit integer to a reference to a structure that has one field, one 32-bit integer field, and do a read-write on that structure, we immediately get an arbitrary caged read and write primitive. So yeah, enough with explaining the bug by Manfred Paul. We'll continue on to the story of how I did variant analysis on this bug to demonstrate an exploit at TyphoonPWN. So yeah, the story goes like something like this. I started looking at Chrome source code from May 27th, just in the hopes of finding any bugs that I could go. And then the demonstration, I should have demonstrated the bug at May 30. So in theory, I have 3 days to write a full Chrome exploit in the renderer. So I opened Chromium code search, but it's a very vast like piles of code. Where should I first look at? Recall that I have very limited time. This means that I need an approach to find and exploit browser bugs in a very simple and efficient way. So how do we find and exploit these bugs in an easy way? The first idea is that we should target bug classes that grant stable and powerful primitives. The second idea is that we should target large, complex, but also readable code. And then the third idea is that we should target under-examined code. My answer to all of these was the WebAssembly garbage collection type implementation in Chrome. As we've seen in the previous bug by Manfred Paul, the bugs have shown extremely strong exploitability. And the implementation is very huge and complex, but still manageable. And a better thing is that we have this helper script, a WASM module builder, which you can just use to create WebAssembly modules systematically. And the last reason is that there seems to be no public research on the actual implementation. There are like PL theory papers on WebAssembly garbage collection and its specs, but there are no analysis on the actual implementation. So yeah, I started looking at WebAssembly garbage collection implementation in Chrome. So to start with this, I first need to recap the previous bug by Manfred Paul. So we take a look into the exact place where the bug occurred. We see like a field named Isorecursive canonical type IDs, which is quite a long name, but it should have a reason for that long name, right? So this field indicates that the isorecursive part indicates that we're using an isorecursive type system. The canonical type IDs means that this is some sort of canonicalized representation of the types. So this naturally leads to the next question of what is an isorecursive type system. So a disclaimer, isorecursive type system may take too long to explain, so I will be as simple as possible. For the theoretical backgrounds, you can check out that paper. The first topic that we'll discuss about in this type system is type equivalence, which means when can we assert that two types are equivalent? In this case, we have these type T1 and T2 and U1 and U2. These two recursive types, the pair of two recursive types look the same because they're just T1 and T2 renamed to U1 and U2. So is type T1 equivalent to U1? We probably want to argue that these are the same, but how do we define this? How do we formally define this? So this is directly from the WebAssembly garbage collection specs, which sort of has this long explanation. But in simple terms, I can explain it like this. We first represent the whole type group as a tuple of types. So the whole type group rec is like a recursive type group rec is a type tuple of rec.0, rec.1, and so on and so forth. And then we replace all of the recursive type references into what we just defined, rec.0, rec.1. And then we compare this replaced type to check type equivalence. So we'll quickly look at a different example where we now have an infinite list of 32-bit integers. In this case, T1, T2, and U1, if you were to unpack this type infinitely, it will just have a 32-bit integer and a reference to the same structure, which again has the 32-bit integer and has a reference to itself. We might argue that these are the same type because the unpacked representation results in an infinite list of 32-bit integers. However, none of these tied representations that I've just explained by recursively referencing them as rec.0 and rec.1 are equivalent. None of these are equivalent, so we consider all of these as different types. The next topic is canonicalization. We saw that what types are equivalent and what types are not. So how do we represent these types as equivalent? The answer is simple. While decoding the type section, we just go through all of the types and see if we have the matching type. If we have a matching type, we just use the indexes that were allocated previously. If we don't have it, we allocate a new index. And this is what the Isorecursive canonical type IDs field contain. The index is a module-specific type index, and the value resulting from it is the canonical type index. The next topic is subtyping, or more specifically, declared subtyping in this case. How do we know that some two types are a valid supertype and subtype relationship? We explicitly declare a type as some supertype of some, subtype of some kind. And how do you know that this declaration is valid? There is a well-known rule for this, so I'll skip this part. But a simple explanation for this could be that for mutable fields, it should be invariant, and for immutable fields, it is allowed to be covariant. So this subtype relationship is also stored in a global canonicalization state named canonical supertypes, where the index in this case is the canonicalized subtype index, and the value resulting from it is the canonicalized supertype index. So we spent about 5 or 10 minutes explaining what all of these isorecursive type system is. So what is all of this for? This is all for doing very efficient cross-module subtype checks. So if you have two module-specific type index from two different modules, we can very easily check if they're equivalent to each other or a subtype to each other. We first canonicalize it by the field as isorecursive canonical type IDs, and then look up into the canonical supertypes vector. We follow up the vector one by one, and if there is a matching index, it is a subtype supertype relationship. If we don't have a match, it was not such a relationship. So yeah, this was a very quick introduction to isorecursive type systems used in WebAssembly type systems. And we'll first continue on to my first bug. So yeah, we had enough of the background. Let's actually find the bug. So at this step, I was just spewing out random ideas. The first idea was that we might be able to overflow the canonical index, which is an unsigned 32-bit integer. But of course, this didn't work in reality because we required too much memory. And more precisely, it required over 200 gigabytes of memory to actually achieve this. So the second idea is that we have this two distinct representation of types. One is a module-specific type index, which is only valid in the context of some specific module. Another is a canonicalized type index, which is always valid in the global context. It's stored in the global canonicalized state. So there are these two ways to distinct types. But the problem is that they're just plain integers. So, which means that programmers could easily confuse them up and then misuse one with another. And another problem is that this canonical type index is not bound by the limit of 1 million. So yeah, to find the bug, I was going very naively and just clicked on the isorecursive canonical type IDs and saw if there are any references. I followed the first reference, and it was an object type checking at JavaScript to WebAssembly boundary for reference types, of course. In this code, we see that we first canonicalize the type into a canonical type index, and then put this into something called a value type. And then if we follow the code deeply into where this value type actually flows into, we see that this is passed down to JS to WASM object. In this place, we also see that we're actually pulling this canonical index back out by calling the methods ref index or heap representation non-shared. So how are we fetching this back? More specifically, where is this canonical index stored into in this value type? We see that we're fetching this from something called a heap type field, which indicates that this is stored in some kind of bit field representation. So if we actually look at what this bit field is made out of, it's made out of 20 bits of data. This 20 value is very precisely determined because 2 to the power of 20 has the value of 1,048,576. So this is enough to store all valid module-specific heap types because there's just 1 million plus some small number of generic heap types. However, this is absolutely not enough to store canonical type indexes because they're unlimited. They're just limited by the host memory. So yeah, this was the big if true moment. And if we're actually able to construct that much canonical types, then we might have a type confusion, which immediately leads to this bug where the canonical type index is truncated to 20 bits. The effect is like a completely broken type checking at JavaScript to WebAssembly boundary, where the intention was to type check the object as a reference to some type T, where its lower 20 bits of the canonical index is a different value of K. The effect is that we're effectively type checking against a different type of reference K, which has this canonical type index value of K. So this results in a universal WebAssembly type confusion from the type K to T. But of course, this is not only the problem here. What if the value K, we don't even overflow the 20 bits, but we have this value K so that this aligns with generic heap types like none types or any types? We immediately see another problem here. We can just set the K, align the canonical type index to a generic heap type like any, and then do a type check against any, and then use that as a specific type T, which is an illegal downcast, but this is what the bug is. So yeah, we've seen these two types of type confusions that might happen, and then the exploit is actually not even worth mentioning here, because V8 Sandbox exploit is exactly the same as what we've previously seen with the Manfred Paul's bug. We immediately acquire arbitrary cage read-write, address of, and fake object, all of the in Sandbox exploit primitives required to exploit a JavaScript engine. For escaping the V8 Sandbox in the competition, I used partition alloc. This is based on a common misconception that the V8 Sandbox contains no raw pointers, but that is still not the case with partition alloc. The problem here is not with a single type confusion, a single misuse of type indexes. We see a much bigger problem, a much bigger design problem that leads the developers to make these kind of mistakes. So in this case, the canonical type is stored in a value type. However, a module-specific type from some module number 1 is also stored in this value type. A different module-specific type from module number 2 is also stored in this value type. So they're all value types, but they mean the different thing. So unless we know exactly where this value type comes from and where we're storing this and where we're passing this down to, we cannot know exactly where this comes from and what this type represents. And we've only seen one case where we confused the canonical type index to a module-specific type index. This naturally leads to the next bug. I've exploited this in a V8 CTF, but it was later found to be exploited in the wild against Android machines. So yeah, the previous bug confused canonical type index to a module-specific type index. Can we confuse this the other way around, So that we're confusing module-specific type index to a canonical type index. Of course, what can happen will always happen. So we just had this patch where we patched some place where we just forgot to canonicalize the module type. The patch is like actually simple. We just see that part where we did the canonicalization on the object type checks on the JS to WASM boundary. We just adding this, which means that we forgot to do this for some random call sites. Exploiting this is, again, extremely simple. We just create a WASM module which exports an exception signature, which are just a function signature with no return types, but the parameters defining what values are stored inside this exception. We export this and then create an exception with the JavaScript API WebAssembly.exception. In this case, in this step, we already have a type confusion. We're type checking this JavaScript to WebAssembly boundary with the wrong types. We're using the module-specific index as a canonical index without actually canonicalizing them. And then we just throw this exception and catch it within WebAssembly and use it as a module-specific type, which again leads to arbitrary WebAssembly type confusion. A bigger problem that we see is not like really about this bug itself, but the problem is how does this bug go unknown and where are even the unit tests? Because each of these steps are designed to do what it's supposed to do. We have the feature of exporting like an exception signature. We have the feature of using it in WebAssembly in JavaScript to create an exception, and we have the feature to throw it and catch it back in WebAssembly. Where are the unit tests? The answer was actually quite simple. We had the unit tests, but the tests did not use WebAssembly garbage collection types, simply because WebAssembly garbage collection extension and the exception handling extension are two different WebAssembly feature proposals. So now we see the type confusion in two ways, from canonical type into module type and backwards. But of course, what can happen will always happen. This happens also for between two modules, two different modules where we confuse one module type to another module's type. We also have another bug which also confuses canonical type into module-specific type due to a broken patch. So in this case, with these two bugs, we've seen the problem with all the problems with value type representation in Chrome's WASM GC type implementations. And then we'll try to see another bug. And this time in their optimizing compiler, turbofan. The story behind how I found this is I was also trying to find this bug in a very naive way. So we had this issue where canonical type indexes were getting truncated into 20 bits. So I wanted to find other problematic truncation issues. When does truncation happen? Well, maybe if we did a static cast into a smaller type, then we might have a truncation issue. And it actually reveals this function, which is a caching logic to cache last accessed memory based in size to optimize sequential accesses into the same memory. And then we see that the memory index here is a 32-bit unsigned integer. And the stored cached memory index is also a 32-bit integer, but we're just randomly casting this to an 8-bit integer. And it reveals that this is really baseless. This is a bug. So when we first access a memory index of value 256, and then access a memory index of 0, this will be considered as the same memory. And then we'll be using the cached memory base and memory length of index 256. But how does this become a security issue? Because if you're actually using the base and the length and always dynamically checking the access against the length, we won't go out of bounds. This will just be a semantics issue where we're writing to another different memory. It also reveals that as turbofan is an optimizing compiler, it tries to do a lot of optimizations. So in this case, we have the offset that the memory write or read operation requested. If this is smaller than the minimum size, as WebAssembly memory can always grow, not shrink, we're aligning the comparison against the current cached size. In the assumptions that the invariance that the current memory size is always larger than the minimum memory size. However, with this bug, this invariant is broken. So computing the remaining size, in this case, the effective size node, overflows. And then we're able to access memory with arbitrary indexes. So yeah, this seems immediately a very appealing exploitation path. We have an arbitrary index out-of-bounds read and write. Is this exploitable? It's revealed that it's not as much as exploitable as I've wanted it to be. The index is limited to 32-bit unsigned integers, and WebAssembly memory is always padded to a full 8 GB range for out-of-bounds trapping mechanism. So wherever we do the out-of-bounds read and write, it will always land at the GAR page, and we won't be able to exploit anything. But looking more deeper into this, I've seen that on Android devices, we don't have these GAR pages. It's because this trapping mechanism is to dynamically check out-of-bounds requests, out-of-bound memory accesses. But in Android, we use Java, and it's really difficult to reason about signal safety issues in Java. So it's probably exploitable if we don't have this GAR page. But again, if we actually look more deeper into this, there's nothing useful to overwrite. The WebAssembly memory always gets allocated after the array buffer partition alloc region, which has nothing after it. But again, if you look closer, and in my case, if I rebooted the test device, I've noticed that this allocation gets fit between the V8 cage and the array buffer partition alloc. So it means that this is probably now exploitable. So we've done in a roller coaster, but in the end, it's probably exploitable. So what are the conditions for this WASM memory to be allocated between the V8 cage and partition alloc so that we can overwrite data in partition alloc? On Android, it's worth mentioning that address is almost always fixed to 1, a randomization bug, and 2, how Zygote works. So we have this fixed allocations, and the V8 Sandbox and both the cage are allocated to an alignment of 4 GB. But the partition alloc region is allocated to an alignment of 16 GB, which grants us the 75% chance to have a gap between them. And this gap is where our WebAssembly memory can be reclaimed with. But also, on this leftover 25% of chances that we're not able to allocate it between these two, we can still probe the memory layout and determine whether this layout is exploitable or not without even crashing. So in this case, we have the maximum amount of gap of 12 GB. We allocate 3 WebAssembly memories, and then starting from each of the WebAssembly memory, we probe the next WebAssembly memory. If it is a WebAssembly memory, we just read 0. If it is a partition alloc, we read some useful data. But what if we don't have this layout? We just, like, in the start, we allocate 4, not 3 of these gaps, and then do the probing 3 times. If we don't find any useful leakage, it means that the layout was not exploitable to start with. This concludes a list of 3 bugs, and we are going to continue on to the list of V8 Sandbox bypasses. A very short explanation of what V8 Sandbox is designed to do is that it's a software fault isolation mechanism to prevent memory corruption from within the sandbox region evolving into arbitrary writes outside of the sandbox. So this means that any bugs, any like JavaScript bugs, should be confined into this sandbox region and should not evolve into arbitrary writes outside of this region. And how the V8 Sandbox works is something like this. We have these 4 GB cage, which all of the JavaScript heap object resides in. But these need to maintain some kind of way to reference data outside of it, which may be stored in like a code space. It could be in your heap allocation. So how this is maintained is we maintain tables, 3 tables in this case, external pointer tables, trusted pointer tables, and code pointer tables. And we just use them by indexing into them in a proper way. The problem is that WebAssembly exposes a lot of these V8 Sandbox bypasses. The reason is that, first, reference types are represented as their full 64-bit pointer, not their like truncated 32-bit representations, across WebAssembly function calls. This means that for all the ways that we could call WebAssembly functions, if we have a signature confusion, this immediately leads to a V8 Sandbox bypass. Another problem is that everything in WebAssembly is an object. Memory is an object, function references are an object, function tables are an object, and so on and so forth. So all of these that could be modified should not be trusted, which is a difficult thing to do. The last problem is that we have this paradigm shift, where the V8 Sandbox and JavaScript should now be considered as something like a user space, while everything else in the browser should be considered as a kernel. So we need to reason about things that are not traditionally a browser issue. For example, we need to reason about things like double fetching from within the V8 Sandbox region. We also have to reason about drivers, which are embedded implementations, in this case Blink, which simply does not exist in V8. So it's also hard to reason about these. The first case will be going through 4 cases and one of its variants. The first case could be seen as a code metadata corruption. In this case, directly we're confusing the signatures. This bug was a missing signature check when importing function tables. So WebAssembly tables are represented in something like this. The red region is the V8 Sandbox region, and the green region is the trusted region, which should be protected from memory corruption. When we import this WebAssembly table, we start to copy all of its entries to a WASM dispatch table. This is sort of the ground source of truth, where this invariant that all of its entries are subtypes of the table's type must always hold. But it's so easy to break this invariant. We can just change the raw type written in the WASM table object to bypass the check when importing the table. Alternatively, we can just keep the type, but go into the fixed array and replace one of its entries. In this way, we can just write a function that has a different signature in the WASM dispatch table and cause a signature confusion. Of course, this is not the only case, and we again have a plethora of lists. A noticeable problem here is that we have cases where we confuse trusted to untrusted references, and we also have cases where the type is just a union of a trusted and untrusted type, which cannot be in any ways trusted. The second case is untrusted indexes, which is also a classical problem with the V8 Sandbox. In this case, again, with the table example, it was previously possible to corrupt the current length and then just do a table set, which will do an out-of-bounds write on the trusted region from the WASM dispatch table. To fix this, we introduced this patch, which does a sandbox check less than check. The problem is that the index and the length is both integers. They're signed integers. So we can just provide something like -1, -2, -7. And then this will also go out of bounds by bypassing this sandbox check. This is, again, also not the only case, and we have more problems with this. The two cases are, the case 3 is broken invariance. This is somewhat similar to what we've seen at the last bug that we've seen, which sort of breaks the invariance and causes problems with, for example, optimizing compilers. The fourth case is transplantation and extraction of trusted objects. This involves replacing and removing references to trusted objects so that we can confuse this trusted object or cause something like a garbage collection in very unfortunate circumstances. We can also augment all of these cases with the double fetch technique. In this case, we're reintroducing the signature confusion bug. In this case, but now we're importing just a function. To import a function, we need to do the type checks. So we first do the type check. We check it by calling the matches signature function, which follows this chain into the trusted reference. But we can just replace the reference to the trusted object. And then when we're actually trying to set the WASM function, we can just replace it into a different function, which causes signature confusion again. We also have the case with the previous bug that we've seen, but in a different feature extension. And then we'll quickly see how other browsers are doing. Firefox made this very weird mistake where any mutability differences in array types are considered a subtype of each other. So this is actually the full exploit that grants you the fake object primitive, where if you just like define it with a different mutability, it's always a subtype of each other, which is remarkably simple but remarkably problematic. Safari just enabled WASM GC from their technology previews, but it still has a long way to go. I want to mention that WebAssembly is also rapidly expanding. There's a lot of new features that introduce a lot of new types, a lot of new completely different designs, and these all contribute to new bugs. Chrome is growing too. It is changing its optimizing compiler from turbofan to turboshaft. So yeah, the conclusions will be as follows. A bug is usually not really a one-off problem. It's an indicator of a much bigger problem. In this case, we've seen that the WASM value type representation is the problematic representation, which leads to a lot of different bugs. We also see that not all bugs are created equal. And for WebAssembly bugs, it's usually easier to write an end-to-end exploit. And we also see from the third bug that every bug, well, a lot of them, is exploitable if you look closely enough. And V8 Sandbox is still not a meaningful security boundary as of yet. I still consider the difficulty increase to be mediocre, but as Google is trying to push this feature out to make it a more stronger security boundary, I have good hopes for it. And the final point is that automated testing often fails to catch up with new features. So it means that there's much more to take a look at. There's much more to write fuzzers and even do manual code audits. And this is just a result of me looking into the WebAssembly code for a month. So I'll do a very quick demo, as I've used up a lot of my time. Yeah, and it just pops calc. It's just as simple as that, and it's very stable. So yeah, that is the end of my talk. And if you have any questions, I would be willing to answer them after this talk. Thank you.